Hello, everyone. Thanks for coming. So this is Eric. He's going to give a talk on stochastic superoptimization for x86 64. He's a grad student at Stanford in CS. He's just finishing his PhD and writing his thesis and shopping for an academic job. So yeah, with that, go ahead.
Okay. Thank you, JF. Thank you, everybody, for coming. Hopefully, by the time future generations are watching this on YouTube, there will be a little pop-up telling you Eric has since graduated. In the meanwhile, I'm here today to talk to you about some of the work that's been going on for the past 3 or so years in my research group. This is joint work with my advisor, Alex Aiken, and my colleague, Rahul Sharma. So to start this talk, I generally like to begin with a bit of motivation that I think just about everybody could get behind, which is that even now, in the era of multi-core, there are still a lot of important application domains out there that are compute-bound. On this slide, I've shown just a couple of examples, whether they be scientific simulations, cryptography, rendering programs. I could go on and on and on with this, but as I'm sure anyone who's worked in any of these areas, or maybe even yourself would agree, obtaining really high performance optimization in these areas is very painful. Certainly there are quite a bit of tools available for mitigating this problem. Especially lately, there's been quite a bit of revitalized interest in compiler research, whether it's domain-specific or otherwise. But what I'd like to argue to you today is that to obtain truly the very best performance, it's still necessary to go in and exploit all of the really dark corners of a hardware instruction set and how it interacts with machine resources. And it's precisely for that reason that today, the very best code that's out there, the highest performance code, is still written by hand by experts in assembly. Now, the work that I'm going to be showing you today is an attempt to improve on this. It's a fully automated method for modifying the assembly implementation of high-performance kernels such that they're able to either match, or as I'll show you in many cases, even outperform code that's written by experts. What I'm going to show you is probably going to seem crazy, and you might start scratching your head and saying, oh, this could never work. Hopefully, by the end of the talk, you'll have hung on to that. You'll still think it's crazy, but you'll leave wanting to tell all your friends about this thing that actually somehow does. So here is a quick outline. I'm going to start out with a description of what stochastic optimization is and how it works. This is going to be absolutely the simplest possible implementation, and it's only going to work for fixed point integer kernels without loops. Then from there, second half of the talk, I'll discuss extensions for handling kernels that contain floating point computations. And again, I will stress that everything I'm going to be talking about today is going to be with respect to loop-free kernels only. In the interest of time, I'm not going to be able to get into work that we've done to extend all this to code that contains loops. But if you are interested, in addition to these 2 papers here, we also have a paper in OOPSLA 2013 which talks about that. So definitely check that out. Meanwhile, here is an example to get started with. On this slide, I've shown 2 implementations of a 128-bit integer multiplication kernel that's used in OpenSSL's implementation of RSA. This is very high-performance code, and really it's only useful insofar as it's high performance fast enough to be invisible to the end user. Basically, the takeaway here is that every instruction counts. To get this code, the code in the center was compiled from C source, which I've suggested on the left here, using GCC with full optimizations enabled. And then the code on the right here was produced using a stochastic optimizer that we've built called Stoch. Maybe eyeball these 2, but please don't stare at it too hard. I'll highlight the important bits for you. They are these. The code, which was produced by Stoch, is 18 lines of assembly code shorter than the code produced by GCC. It's 60% faster, and what's really cool is that it's even slightly faster than the handwritten assembly that shipped with the library at the time we originally performed this experiment. And the reason why that is that the Stoch code takes advantage of a number of very target-specific optimizations. Among other things, it permutes its inputs in non-trivial ways and moves them into distinguished registers to take advantage of fast hardware intrinsics, which completely eliminate control flow divergence and increase throughput, which is all very cool, and I'll come back to that. But for now, what I really want you to take away from this example is this. That code was produced completely automatically, and I'm going to show you how. So to explain how all of this works, first I'd like to develop a little bit of intuition for how we've gone about formulating this problem. Here I've drawn a sketch of what I'll call the abstract space of all possible loop-free assembly programs, which for reasons that I hope will become clear in a moment, the community is taken to referring to as rewrites. This is a very large, very high dimensional space, and it's much larger than the two I'm using here for the sake of visualization. And in fact, for me to even be able to draw this box around it at all, I have to make a qualification to you that all of the programs in this space have fixed length. Now in this space, programs correspond to points. Here's one of particular interest. This is the code that I just showed you in the center of the previous slide, which was produced by GCC 03. And because this is the code that we're interested in optimizing in particular, we refer to this point in particular as the target. And now, because we're interested in optimizing this code in particular, what I can do is I can go ahead and I can partition this space into two disjoint sets. In blue, I've shown the set of rewrites that are functionally equivalent to the target. And in white is everything else. And I've drawn several of these blue regions here to stress that there are actually many interestingly but also distinct ways of implementing this kernel. As I just suggested to you, the code that's produced by Stoke is often a separate region over here on the left. Because the algorithm that it implements is actually quite different from the one that the code produced by GCC uses. To help get an intuition for what I've done here in this picture, it might help to think about a slightly higher level optimization task. Imagine if you were sitting down and optimizing sorting routines. One of these regions might contain all implementations of bubble sort, modulo optimizations, and another might contain all implementations of quicksort, for instance. If that helps, great. Take that intuition and now scale it down to the level of loop-free x86 kernels. And remember, this is just a visualization. So at some point as we get deeper and deeper into the details, this will break down a little bit. But for now, it's good. So if you're comfortable with that, an equivalent way of visualizing this idea is with a binary indicator function. So here I've shown the value of this function, or such a function, along a slice through the space, which passes through the two codes that I just showed you, the Stoke code and the GCC code. The way I'm drawing this function is 0 for all points that correspond to functionally correct rewrites, and it's non-zero otherwise. And even though I'm just showing you a function through a slice here, this function would be defined for all points in the space. And now if you're comfortable with the idea of a function being defined over this space, then what I can do is suggest to you that there are many other possible functions for measuring the quality of these points. Some simple examples would be code size, expected power consumption, expected number of cache misses, expected runtime. In the formalism I'm showing you here, the only feature that any of these functions would share is that lower values correspond to better rewrites. So here's a hypothetical example of an expected runtime function. You'll notice, in particular, the lowest point on the curve corresponds to the code discovered by Stoke, indicating that this would be the fastest code along this slice. Whereas the GCC code is good, but it's only a local minimum. And here I've also noticed that just because a rewrite is functionally correct doesn't guarantee that it'll have a low performance cost. So in general, what can we expect? We can expect that these functions will be quite poorly behaved. They'll be sharply discontinuous, highly non-convex, and they'll just be full of these local minima. So, given this formulation of the space, what I'd like to do now is make a non-standard, but what I hope is obvious assertion, which is that program optimization is really nothing more than a very high-dimensional search problem. So, given a point of interest, this target program, the goal of any program optimizer is to just produce a rewrite with the lowest possible performance cost, which is also functionally correct. In the context of this picture here, the goal is to find the lowest value on the blue performance curve, for which the green correctness curve is 0. That's the way we think about this problem. Before I jump into how we our solution, let me first just take a moment and try to place this in the context of existing approaches. Here, I've shown the behavior of a traditional optimizing compiler. What we have is a simple syntax-directed translation. We'll produce something like this unoptimized LLVM code here on the right. And the application of standard semantics preserving techniques like dead code elimination, constant sub-expression elimination, what have you, will eliminate most of the inefficiency of this code and produce something like this LLVM 03 code here. But this is, of course, complicated, and two compilers often won't agree on the results. So here I've noted that LLVM with full optimizations isn't quite identical to the code produced by GCC with full optimizations. And regardless, None of the standard optimizations that we're familiar with, whether they be target dependent or otherwise, are sufficient for escaping this region of points on the right here and producing a program that looks something like the code produced by Stoke. Completely a different approach to this problem, which is guaranteed to work in the long run, is to simply guess and check every possible implementation in this space. This sounds sort of wild, but it works surprisingly well for RISC instruction sets, and even in some cases for CISC machines. In the past, my advisor Alex and one of his students were able to produce some pretty interesting optimizations by building a database of all possible x86 program fragments of up to 3 lines of code, that was the upshot. The downshot was this took over a compute month to do so. And at 11 lines long, the code produced by Stoke on the left here is well beyond, fortunately, the scope of what we'd hope to discover using only this technique. One way to address this scaling issue is through the use of expert-written equality-preserving transformations. So the idea here would be beginning from any one of these correct implementations, a known correct implementation. These rules would be repeatedly applied to enumerate a set of points that ideally would cover most of these regions. Then this much smaller set could be traversed in a reasonable amount of time, and the most performant code could be returned as a result. Well, this works quite well as well. The key issue here is that missed axioms correspond exactly to missed optimizations. And what's even worse than that is the code that's produced by Stoke has this actually really interesting property, which is that there is no sequence of small equality-preserving substring transformations that will ever be able to connect it to any one of the programs on the right here. Turns out that the only transformation that will accomplish this is the one that produces the optimal code all at once, which is great. But if we had that, we wouldn't have a problem to solve to begin with. So, well, this is good. Doesn't quite work for us. Lastly, just a quick nod here. Program synthesis is an approach that removes this dependence on expert-written axioms in quite a few ways. Unfortunately, in the interest of tractability, most of these programs operate on high-level IRs that use bit vector calculi rather than directly on executable assembly. And as a result, they have no way of reasoning directly about the performance properties of the code that they ultimately produce. So although these techniques do work, and they work quite well and quite often, they can be thought of as throwing a dart, which will land somewhere on this picture in a correct region. But beyond that, there isn't anything we can say about the performance. So finally, this brings me to our approach, which is to overcome these limitations by using random or stochastic search. Thus the title. Our approach is similar in some sense to brute force enumeration in that it's content to experiment with incorrect implementations. However, it sacrifices completeness in the interest of tractable runtimes. So the idea is pretty simple. Here's how it works. First, a set of synthesis threads are initialized to random code sequences, and random walks are used to discover as many of these different regions of correct implementations as possible. Not all of them will find them. Some will just wander off. And then next, for as many of these regions as we were able to find, a new set of random walks are performed in an attempt to discover the most performant code in each region. And what's sort of crucial here is that nothing constrains these walks to stay within a region that they're initialized to. So although some leave and never come back, like this poor guy on the left over here, many are actually able to discover useful shortcuts that experiment with temporarily incorrect solutions, like the one on the right here, which temporarily leaves this blue region. And maybe even more interesting than that is that it's often the case we find that it's these threads in particular that end up producing the most interesting results. Get more into that in a little bit, but for now, that's the big idea. Hopefully I've given you some intuition as to how all of this works and gotten you excited about it. So now let's get into some details. So at a high level, for this to work, as I've described it to you, we need two things. We need a search procedure for performing the random walks, and we need a formal method for encoding and combining these correctness and performance functions that I just showed you. It turns out that these two issues are pretty tightly coupled. But what I'll do is I'll discuss each in turn. First of all, for search procedure, we use MCMC sampling, which, along with a host of other random search techniques, is more or less the only known solution method for very high dimensional irregular search spaces, like the one that I've just showed you. Essentially, all this is a random process for drawing samples from a function where a symbolically closed form representation isn't available. You can't write out the semantics of the function mathematically using some nice notation. Turns out, though, that this property is crucial because, in general, we wouldn't expect to ever have a nice representation of either the correctness function or the performance function that I just showed you. How this works is it was actually originally developed as a technique for sampling from probability distributions. But it turns out that it can be applied to search because it has a pretty interesting property, which is it draws samples, or in the context of search, it visits a rewrite in proportion to the value of the cost function. So as I've shown here in this example, MCMC Sampling would draw samples from the function I've drawn on the left here in proportion to the histogram that I've drawn on the right. The higher values are visited more frequently than the lower values. I'll say more about cost functions in a second, but for now, just remember that lower costs correspond to better rewrites. So what this means is that if we take our cost function and negate it, we can guarantee that lower cost, higher quality rewrites get visited more often than higher cost, lower quality rewrites. And although it's true that we don't get any guarantees with respect to convergence rates, what we find is that for all the application domains that we've looked at, this turns out to work quite well in practice. So here is a high-level sketch of the algorithm. This actually is more or less the algorithm. We start by selecting an arbitrary point in the space. For synthesis, this is any random rewrite. And for optimization, this is any rewrite from a region of one of those blue regions of correct implementations. And then for as long as we have the computational budget to do so, we just repeat. We propose a random modification to the current rewrite and evaluate this cost function. If the cost function has decreased, meaning the code has either gotten faster or more correct, that's great. Modification is accepted and the current rewrite is updated. But if the cost function is increased, meaning the code has gotten either slower or somehow more broken, with some probability, which I'll call an acceptance probability, depending on how bad that increase was, it might be accepted anyway. And that's all. When time is up, we simply look back at all the samples we've taken, and we return the lowest cost sample that's also correct to the user. In practice, there are some nasty details, which I will gloss over rather quickly. If you're interested in the details, I would recommend you, once again, to our page. Right. So welcome back. You missed some stuff, not too much, I guess. What was I saying? Right. Before I go on, I will stress this last point. There's no magic here. For everyone who missed what I said, you can just assume it is magic. In principle, there are many other randomized search methods that we could apply to this problem. In our experience, MCMC sampling is just a nice trade-off point between experimental results and complexity of implementation. So here are the random transformations used by our implementation of MCMC sampling. As required, these are all ergodic, symmetric, and importantly, no expert intuition is built into them. These moves are simple to implement and satisfy a well-known sort of black magic design criteria for MCMC sampling, which is that they strike a balance between inducing small local modifications and large global modifications. In the center here, I've shown a fragment of a rewrite. Remember, a rewrite is a point in the space of programs, and the goal of one of these transformations is to move to an adjacent rewrite. So for each move here in a second, I'll highlight the changes in red. First, insert moves create a new random instruction at a random location in the code. So here we have a new integer multiply instruction added. Delete moves remove a random instruction. Maybe it turns out we didn't want this move as badly as we thought we did. Instruction moves will replace a random instruction with a brand new replacement. So in this case, the AND has become a shift arithmetic. Opcode removes replace only the instruction mnemonic for a random instruction in such a way that the new opcode is correct given the types of the old operands. Operand moves are similar except with respect to operands instead of opcodes. And finally, swap moves will exchange the location of two random instructions. Hopefully with a little bit of thought, you can convince yourself that these transformations are alone are sufficient to transform any rewrite into any other. Good. Now on to cost functions. Here I've shown the cost functions used in our implementation of Stoch. We use two, one for each phase. For synthesis, which is the search for regions of correct implementations, we use just the correctness function. Random walks start from an arbitrary point in the space, and they attempt to discover zero-cost correct rewrites which we believe to be closely surrounded by other correct rewrites. That's these blue regions here, again. And for optimization, which is a search for the best rewrite in each of those regions, we use a cost function, which is a weighted sum of both correctness and performance functions. And it's combining these two functions that allows the search procedure to trade correctness against performance and to experiment with these shortcuts that I mentioned a second ago through temporarily incorrect implementations. I'll talk about our implementation of both of these functions in turn. In both cases, as I suggested, the primary design criteria was computational throughput. And that's because, again, MCMC sampling works only as well as it's able to maintain a very high proposal throughput. So to get started talking about that, in principle, a binary indicator function that I've already shown you would suffice as a correctness function. But in practice, MCMC sampling is much more effective when it's applied to smooth cost functions. So though in the limit it's guaranteed to explore past even these very sharp discontinuities, in practice convergence rates are much faster for functions that are characterized by smooth transitions like I've suggested on the right here. As a result, instead of simply classifying a rewrite as correct or incorrect, it's preferable to be able to quantify partial correctness. Okay, so how do we do that? For x86 assembly programs, a fast method for doing this is to simulate both the target and the rewrite on identical inputs and just compare the results. So here I've shown an example of an input, which I'll refer to as a test case. This is simply a snapshot of an x86 hardware execution context, or slightly more formally, it's an assignment from live-in hardware locations, whether they're the general purpose registers, the SSE registers, or locations in memory, whether they be on the stack or heap. Let me just jump in. Can they can hear me now? Okay, good. Once we have a test case, simulating both the target and the rewrite on that test case will result in two distinct machine states, one for each execution. And then given those two states, what we can do is produce a fast approximation of correctness by just comparing the bit vector values in the live-out memory and register locations in each. And in order not to overfit a single input, we can generalize this approach to as many test cases as we like. Here's a simple method for comparing bit vectors, which is to sum the number of bits that they disagree on. In the example on the left here, I've shown the bit vectors produced by a target and a rewrite for a subset of the general purpose registers, just AX through DX here, and assume that only register AX is live out for this particular example. Using this method, we would assign the rewrite a cost of 3 for 3 incorrect 0 bits. So whereas the right answer was all 1s, it got 0, 0, 1, 0. All 3 of those zeros are incorrect. And the plot on the right here shows the best result obtained over time using this as a cost function for a synthesis thread on the OpenSSL kernel that I showed you at the beginning of this talk. For comparison, I've also shown the results obtained by a purely random search thread on the top here. Takeaway is that after 30 minutes, the search failed, meaning it was unable to find a zero-cost correct rewrite. So although this is perhaps intuitive and close to what we need to make this work, there's still something that needs to be changed before it actually does. And sort of the thing that we're missing is captured in this example here, which is something interesting to note about these two bit vectors is that the rewrite actually has produced the correct value, this string of all 1s here, only it's put it in the wrong location and registered DX. And what we can do to account for this is to define an improved version of this function, which returns the minimum bit vector difference across all of these registers, and adds a small penalty, in the case of this example, just 1 for a correct answer or a near correct answer in a wrong location. And in this case, we actually get, I would argue, a much more appropriate, almost perfect cost of just the penalty 1. Figure on the right here now shows substantially improved performance. And in fact, with some small modifications to account for what it means for a rewrite to produce undefined behavior, like a seg fault or floating point exception, this is the cost function that we use in our current implementation of Stoch. As I suggested earlier, our primary design criteria here really is speed, so quite a bit of engineering work has gone into making this computation as efficient as possible. I would love to say lots more about this, but I'll have to reserve that for conversations offline. Here I'll just summarize the results. Our current implementation of Stoch has a JIT assembler for the entire x86 64 instruction set, which lets us simulate rewrites directly in hardware. In addition to guaranteeing semantic correctness, the hardware is a faithful representation of the specification. As opposed to what you would get with a potentially buggy software emulator, this is also quite fast. At peak throughput, even after you take into consideration the sandboxing, which we have to inject to guarantee that natively executing random code sequences doesn't crash our machines, this implementation is able to safely dispatch between 1 and 10 million of these test cases per second. That's correctness. Now performance, which will be brief. In contrast to equality, the performance metric used by the optimization phase of our approach is relatively simple. Because our implementation of Stoch is concerned with minimizing expected latency, rather than attempt to measure performance directly for a particular rewrite, we just look up the expected latency of every instruction in the rewrite and sum the results. And of course, this ignores almost all of the interesting second-order effects that are introduced by a modern CISC machine. Hardware engineer who's watching this is probably cringing. It turns out for the kernels that we look at, though, this seems to work pretty well in practice. Finally, I will note that because our goal is correct code and it's necessary to formally check correctness and performance, there is a little bit more work that we have to do. For guaranteeing correctness, we take a relatively standard approach, which is to encode both target and a rewrite as SMT formula, and use an off-the-shelf solver like Z3 to query for inputs that cause the two functions to disagree. If the proof fails, we can just back the search up to the last rewrite that had a verified, actually correct equality cost of 0. And as a useful side effect, if the search fails, a counterexample that's produced by a failed proof can actually be fed back into the system as a new test case, and as a result, improve the predictive powers of the correctness function. And to deal with performance estimation error, for our performance function, we just record the top N% best scoring rewrites obtained during optimization, and we either hand them all back to the user, which is already something that a traditional compiler can't do, give you more than one interestingly distinct implementation, or we just compile and run them on an actual representative workload and return the truly fastest result to the user. So that is the whole idea from start to finish. Now that you've seen how it works, here's a demo of Stoch being applied to that OpenSSL code that I showed you earlier. In this video, Stoch is going to begin execution from an empty code sequence and attempt to synthesize a functionally correct rewrite. On the left, I'll show the best code discovered so far, and on the right, I'll show the current code that it's evaluating, along with costs associated with them above. This is a little bit faster than real time, given our current implementation, which takes about, it's still running, but it's a video, and I get nervous every time, like it's not going to finish. I know it's going to work. Yeah, so this is with reference to our current implementation, which can do this in about 2.5 minutes. In addition to this code, we've also evaluated our fixed point implementation, the one I've just described to you, on a number of other kernels. In the interest of time, I won't dwell on these too long. I'll just summarize them quickly. From Sumit Gawani's work on program synthesis, we have a benchmark of 25 loop-free kernels that range in complexity from turning off a bit in an integer to rounding up to the next highest power of 2, which is actually more complicated than it sounds. It takes about 9 instructions to get it right. From the BLAS package, we have the body of Saxby to demonstrate our ability to reason about vector intrinsics. And from Alex's student Saurav Mutsal's work, we have some linked list benchmarks to demonstrate our ability to reason about programs that modify the heap. I won't, as I said, I won't dwell on these results in the interest of time, other than to say that the runtimes for the synthesis and optimization phases of our tool, which I'm showing on the top here, are all tractable, and that starting from code compiled with LVM0, we're able to produce rewrites either match or outperform the code that's produced by GCC03 and ICC03, and even in some cases, for about more than 20% of these benchmarks, outperform expert handwritten implementations. One thing I will note very quickly is that this plot is actually a little bit out of date now. This is from our 2013 submission Atlas. We have work in submission now where we've revisited these experiments, and we've basically reproduced the results and brought the runtimes down by over an order of magnitude. So as before, where some of these benchmarks can take up to 30 minutes, now we can reproduce the results in about 2.5. Before I wrap up this part of the talk, I certainly don't mean to leave with giving you the impression that there aren't interesting problems that need to be solved. Here's a simple failure case that we can't synthesize a correct implementation for, which is this rounding up to the next highest power of 2 benchmark. To sort of give you an intuition for why this is, in the table on the left here, I've shown sample outputs produced by a correct implementation of this function and an incorrect function that always returns 0. So For the inputs on the left here, the correct implementation returns the result in the center. The incorrect implementation will always return 0. It turns out that this incorrect function is extremely attractive to a search process. It's both simple to discover, and it's only ever wrong in a single bit. And it's also immediately adjacent to just about every single program. All you have to do is blow the program away and replace it with something that returns 0. Developing techniques to escape from strong minimum of this form to discover the true global minimum is something that we're currently looking into. And it wouldn't be correct of me to say we can't do this, because now we can do this. But if you're interested in how we do it now, I'd be happy to talk about it offline. Okay. That said, moving on. Up until this point, all of the optimizations that I've shown you have preserved complete bitwise correctness. Unfortunately, and that's all well and good for fixed point computations. There are many interesting fixed point computations out there. Unfortunately, this is very difficult to do for floating point computation. Performing optimizations that also preserve correctness, full bitwise correctness, is a task that compilers and experts alike are notoriously bad at. But maybe surprisingly, it was surprising for me, it turns out that for many interesting applications, this is an unreasonable goal to aim for in the first place. As a simple example, there's no reason I would argue why a compiler should insist on preserving a full 64 bits of floating point precision if it's with respect to a computation that takes inputs that are given to it by scientists who only know the values to 2 significant digits. What's the point? What I'd argue we'd really like to do instead is perform optimization in the presence of weakened requirements for correctness, that transformations don't have to preserve floating point semantics exactly as written. So to get you thinking about this idea, here's another example. If you got through the other code slide and you're excited to try to get through this one, please don't do that. This one is just horrible to look at. The code on the left here is a handwritten implementation of the exponential function, which is based on a 12-stage Taylor series expansion. The expert who wrote this cared enough about performance that he already ripped out support for certain special floating point values like not a number and infinity. But he did ensure that for well-behaved inputs, this is correct up to 64 bits of floating point precision. The code on the right here, again, was produced by Stoke, and it's based on something like a Taylor series expansion, only it contains strange constants. Multiplications have been replaced in many cases by adds, terms have been dropped, terms have been added, and there are in many places rotates and shifts, which to the best of my knowledge approximate arithmetic, and are also slightly faster, interestingly. Once again, the takeaways here are the Stoke code was produced completely automatically. It's also 25% smaller, and it's 57% faster than the original implementation. And you say, okay, that's great. Sure, I can generate random code, and it would probably be faster, too. But what's really cool here is that when we took this code and we embedded it in a high-performance scientific simulation, we were able to produce a 27% overall simulation speed-up. And in spite of this strange-looking implementation, for inputs in the very small range that were exercised by that simulation, the results were correct to within a very small error bound, much smaller than the maximum acceptable error that the scientists who were running this simulation specified as the bound beyond which results can't be trusted. And so why is this possible? It turns out it's because the uncertainty that's introduced by slightly incorrect results in this kernel is negligible compared to the uncertainty which is introduced in the course of normal application execution elsewhere. So cool. So to explain how Stoke was able to generate this code then, here again, I've drawn the abstract space of all possible programs. However, this time, there's an important difference, which is that notice that the rewrite produced by Stoke isn't in a blue region at all. It's over here in the center of the slide, and that's because, strictly speaking, it's not correct. For floating point codes, there's another difference here. The optimization task is actually a little bit worse or a little bit more difficult than what I showed you earlier. Most floating point instruction sets are very sensitive with respect to low-level transformations. What that means is that even some of the most basic arithmetic identities that you would expect a compiler to have at its disposal, like the associativity of multiplication and addition, they don't actually hold. And so what this means is that for floating point codes, these blue regions here are actually very small. Each would contain an implementation like a Taylor series expansion, or a Chebyshev expansion, and a very small handful of semantics preserving variations on that idea, which actually can hold with respect to the instruction set. But once a traditional compiler has done its job and applied those transformations, there really isn't much work left to be done here. Again, what I'd argue we'd like to do is to make qualifications with respect to what it means for a rewrite to be correct. We like to say things like, this rewrite only has to work for positive inputs. I'm never going to run this code on negative inputs. Or this rewrite only has to produce results that are correct up to 30 bits of floating point precision. I'm never going to have enough significant figures to know that value to that precision. In this picture here, I've represented these qualifications by expanding the borders around each of these blue regions. And importantly, what I've also done is shown that if we're able to produce these qualifications, the code that's produced by Stoch, which used to be all by itself, is now part of a qualified correct region of its own, along with its nearest, strictly speaking, incorrect, but for the sake of this example, correct enough neighbors. And if we're lucky enough that our application domain allows us to make qualifications long enough, what we find is that in many cases we're able to join the regions, the blue correctness regions surrounding both the original expert code and the code produced by Stoch. And if we can do that, a random walk beginning from 1, so that's not synthesis this time, it's just strictly optimization, only beginning search from an expert written code, we're able to produce the optimization, the Stoch code that I showed you a moment ago. So again, that's the intuition. And now, with the remaining time, I'd like to get into the details of how this works. So what do we need? In this case, we need 2 more things in addition to what I showed you earlier. Aside from these changes, everything else is going to stay exactly the same. First, we need a new correctness function, one that encodes a formal version of what it means for a floating point program to be sort of correct, given a test case. And second, we need a new formal verifier to ensure that a Stoch rewrite is sort of correct for all possible program inputs. For measuring partial correctness, we use a metric called OLPS, which measures the distance between a real number, like E on the number line here, and the closest representable floating point value. I've drawn these as circles in this cartoon here on the bottom. And when this metric is applied to do floating point values, as I've shown here, it can be thought of as simply counting the number of representable floating point values between the two. Turns out this is widely used as a measure of error in the scientific simulation community as a definition of what it means for a floating point result to be correct. Half is considered to be a gold standard because it's as close to mathematically precise as a representation will allow you to be. But that's in practice, very difficult to obtain, and most applications settle for 1 or 2. And they often won't agree on which inputs those 1 or 2 are with respect to. So one implementation might produce an OLP error of 1, where for the same input, another implementation might produce an OLP error of 2. In just a second, I'll show you how we can obtain some very cool results by substantially weakening this requirement and saying we'll settle for up to millions or more OLPs of error. Nonetheless, with this definition, the modifications are pretty minimal. We execute the target and rewrite just like before, sum the OLP error between values and live outputs, and round OLP errors below a user-defined threshold down to a correctness value of 0. The real challenge in this application domain is in guaranteeing that a rewrite is correct within an error bound. Even though equivalence of loop-free codes is decidable, decision procedures for testing floating point equality don't generally scale beyond 5 lines of code, which is far below the length of the benchmarks that we've come across. Abstract interpretation techniques, generally speaking, can't prove complete bitwise, let alone partial correctness for many of these benchmarks. And neither set of these techniques can handle mixed, fixed, and floating point kernels. I could say a lot more about this. The bottom line is simply, for purely fixed point codes, we have off-the-shelf solutions that we can use to guarantee that an optimization is correct for all inputs. If codes contain even the slightest amount of floating point computation, there's no standard technique that we're aware of for solving this problem. So rather than attempt to prove that an optimization is correct within an error bound for all possible inputs, what we instead do is try to produce a high confidence claim that we believe this to be true. Encoding this goal is easy. We just define an error function that counts the OLP error and live outputs between the target and the rewrite on a test case. And once we have that encoding, all that remains is to solve now for the maximum value over all possible test cases and check that it's below the user's upper bound. In general, we could expect this function to be poorly behaved and have no closed form representation. But, as I hopefully just convinced you, that's precisely the sort of problem that MCMC sampling is well suited to. In fact, compared to the formulation I showed you a moment ago for searching through the space of x86 code sequences, Formulation for this domain, searching through the space of all test cases, is much simpler. All we need is a single transformation, which I've shown here for exploring the space of test cases, one that randomly modifies the value of a live-in value. Using this transformation, for as long as we have the budget, we just, as before, repeat the following. Propose a new test case and execute the rewrite. If the error has increased, that's great. We accept the change. We're looking for test cases that produce the largest errors. If not, if the error has decreased, some probability, depending on how much the error function has decreased, we'll accept the change anyway. And as before, when time is up, we check the maximum observed value, see whether it ever exceeded the bound provided by the user, and then we either return success or fail with a new test case. Now, there's a new problem here, which is the question of when to terminate search. It turns out there are several well-known methods for checking whether a sequence of samples has uniformly explored the entire domain of a function, as I've suggested in the figure on the right here, as opposed to the one on the left. And if these tests pass, what that means is we can be relatively confident that MCMC sampling has discovered all of the local maxima of that function, because it's explored the entire domain, and we know it takes the majority of its samples from points that produce the largest values. And if we can claim with high confidence that we visited all of the local maxima of the error function, then I can also claim to you with relatively high confidence that we visited the global maxima. Of course, this is only a claim, and this technique would be inappropriate for safety-critical applications, where formal bitwise correctness or formal correctness with respect to a user-specified upper bound is absolutely required, like, you know, checking the launch codes or whatever. But for plenty of real-world applications where regression testing is the de facto definition of correctness right now, this works well, and I would argue is a significant improvement over the state of the art. So, in addition to the exponential kernel I just showed you, we also evaluated our floating point implementation on a high-performance implementation of the C numerics library and a ray tracer. And before I finish up, I'll quickly show you some of those results. I'll start out with libimf. This is Intel's implementation of math.h. Kernels in this library are all written by hand, and they're about 2 to 3 times faster than the equivalent GNU implementations. And here I've shown optimization results for 3 of those kernels, sine, log, and tangent, from left to right. In each of the plots on the top here, I've compared lines of code against performance improvement. Lines of code is the dark blue curve. Performance improvement is the light blue curve. And a vertical slice through any one of these curves corresponds to the optimization that was obtained for a different user-specified maximum ULP error. So from all the way on the left here, 0 ULP error, meaning give me a rewrite which is bitwise equivalent to the target code that I'm giving you, to all the way on the right, which is 2 to the 64 bits of ULP error, which says, I don't care what you give me, I'm going to give you back return 0 because it's all the same. So, of course, the performance is through the roof, all the way on the right. But what I want you to take away from this is that as we move to the right and increase this maximum acceptable ULP error, we get a performance improvement and a reduction in code size, and it smoothly interpolates between both sides of the curve. It's not as though we get the win all the way at the end when all of a sudden the user doesn't care about what we're giving back then. What we've effectively done here is generate substantially faster arbitrary precision versions of this library that smoothly interpolate between double precision, single precision, half, all the way out to Boolean precision, if that were something that you could, for some application, be interested in. Below these 3 plots here, all I've done is I've superimposed the error functions for each of the points along these curves up top here. I've just done this to suggest to you that although the error functions are complicated, they're not particularly perversely poorly behaved, and our validation technique terminates quickly with a maximum value. Here, I've shown the result of applying Stoch to the implementation of a ray tracer. Even before we consider optimizations that sacrifice correctness, Stoch is able to obtain a 30% speed up over the original implementation just by performing bitwise correct optimizations like the ones that I showed you in the first half of the talk, which improve the performance of vector kernels. The image that I've shown on the left here is actually pixel for pixel identical to the image that's produced by the original implementation. But again, it's 30% faster than the original. But there's more to be done here. It turns out that the depth of field blur in this image, which is the blurring on the horizon there, is produced by repeatedly randomly perturbing the viewing camera angle in the innermost loop of this code. And what we can do is apply Stoch to this kernel and set the maximum acceptable ULP error appropriately low so that we can produce code that's close to 2 times faster than the original implementation. And although this code doesn't exactly obey the floating point semantics which were originally specified, the results are almost completely imperceptible. On the right here, I've shown a few pixels highlighted in white that disagree between the 2 images. And I would argue that had I not shown that to you, I don't think you could tell the difference between the 2. And just to wrap up, as a fun example of how you can get exactly what you asked for without realizing what it was that you asked for, if the maximum acceptable ULP error is set above the variance of the random noise that's used to introduce the blur, then Stoch is content to eliminate most of the kernel altogether. In fact, it eliminates the entire kernel. So if the ground truth implementation is perturbing the camera a small bit, and you tell Stoch, well, I don't care about floating point errors above a certain value, it will say, well, then not doing anything is equivalent. It gets me within that error bound. The code is, as you would expect, a lot faster because it's not doing anything. But in this case, the error is noticeable. You can see the blur on the horizon here, which used to be quite prominent, has now completely disappeared because the kernel that induces it is gone. And as a result, just about every pixel is wrong in one way or another. So here on the right, again, error pixels highlighted in white. Just about every pixel is white. So with that, I suppose I should probably wrap up. I will conclude and again make the claim to you that for many interesting real-world application domains, even a single assembly instruction can still make a difference. Our approach to this problem is a new one. It trades completeness in favor of stochastic search, and it's able to experiment with temporarily incorrect optimizations in interesting ways to obtain results that either match or outperform the code produced by production compilers, and in many cases, also the code produced by expert assembly writers. I also want to step further than that and propose that for applications that can tolerate a loss of precision, this technique is also a viable method for sacrificing correctness in favor of even smaller code and still higher performance. There's lots more to this story, which unfortunately I don't have time to get into. There's the extensions to loops, which I mentioned briefly at the beginning of the talk. And there's also work that we're currently pursuing for automatically synthesizing hash functions, random number generators, malware attack strings, all sorts of cool programs. Just to name a few, but for now, let me just say thank you. I really appreciate you coming to this talk, watching on TV, wherever you are. And I'm happy to take questions or hang around as long as people are interested afterwards to chat. Thanks.
All right, thanks, Eric. So if you have questions, I have a microphone.
So one thing that went by that I did not understand, for correctness, you're going to, for just on the fixed point computation, not the floating point. For correctness, you go ahead and actually run the program on test input. Mm-hmm. But for performance, since you are running it on the actual machine, why don't you just time that for performance rather than approximating it by summing latencies?
Two answers to, so thank you, good question. Two answers to that. The first answer is, in order to obtain an accurate enough performance estimate, we would have to run the kernel sufficiently many times that the overall throughput of the algorithm would drop. And second answer, even if that weren't true, we're not executing the kernels natively. We're executing the kernels along with instrumentation that will sandbox that. So you wouldn't be getting a performance estimate of the kernel. You'd be getting a performance estimate of the kernel sandbox.
You have the questions?
Why the specialization with respect to loops? You mentioned that your algorithm doesn't handle it yet and that you're working on it, but do loops not fall naturally into the Markov Chain Monte Carlo framework? If you're just permuting instructions, all of the loop instructions should be there as well, yes?
Mm-hmm. Yeah, certainly. So again, there are two answers to that question. The slightly, well, let me say it like this. There are always going to be two parts to this story. There is the search part of the story, and then there is the formal verification part of the story. You're certainly correct that the search part of the story requires almost no modification, right? The instructions which induce looping behavior, jumps, labels, what have you, are in some sense no different from an add instruction or a multiply instruction. So modulo some additional implementation in the sandbox that we use to execute our programs natively, which will check for infinite loops. Yes, we could just be using the exact same search procedure that I showed you with a couple of small changes to the proposal mechanism to search through the space of looping programs. The real complication is once you go to the formal verification side of the story, checking for equivalence of programs with loops is no longer decidable. So you're never going to have a completely general purpose solution for this problem. So what's necessary is both coming up with a clever mechanism for checking certain types of loops and then biasing search towards finding optimizations of that flavor that you have some hope of verifying. Now that said, for certain application domains, I would argue it's perfectly valid to just take the validator and throw it out the window. Again, the definition of correctness is some guy wrote a couple of regression tests and he runs them while he gets coffee. So we're probably running more regression tests in search than this guy is, so could work just fine.
Thank you.
Sure.
Why isn't insertion and deletion sufficient for the set of transformations?
Well, with respect to what?
You had transformations for changing the opcode.
I see. You're absolutely right. Insertion and deletion moves are the only transformations you need to explore the space. And in fact, when I I glossed over an argument for ergodicity, the ability to transform any code sequence into any other. The proof is just that. Take the original code sequence, delete everything, and insert everything else. It's just an empirical optimization. In practice, people have found that MCMC sampling works well if you can mix small transformations and large transformations. So there's redundancy in there. An instruction move you could decompose into an opcode move followed by operand moves. In some cases, it seems to make the search seems to converge faster when it has the ability to make a large jump by proposing an instruction that's almost correct and then tweaking the operand. Oh, this is a familiar face.
If you're going to, I guess I have to ask this, if you're going to generate an optimization that's useful in a general library context, which means that it's also going to be usable in a multi-threaded context, you have to work, you presumably have additional correctness concerns, right? Because in addition to ensuring that you get bitwise the correct output, you also have to make sure that you're not updating, you're not overwriting data that you weren't supposed to, even if you write the same bits back.
Yes, that's absolutely correct. So that's a weakness. That's a weakness that you've identified in what I would argue is a strength of our approach, which is right now our tool is completely compiler agnostic. Use whatever tool chain you like, you spit out a binary, and then we'll take a look at that binary and we'll optimize it. Now, there's plenty of extremely useful information in whatever compiler you use, such as a volatile annotation, which has completely disappeared. And if we don't have access to that, then we're missing a sort of a crucial piece for this verification puzzle. Certainly, we could look towards techniques for, in some cases, we could verify correctness in the absence of those annotations. An alternate approach might be to produce an optimization and not just produce an optimization as correct for all possible inputs, but produce an optimization and tag it and say this optimization is correct under the following assumptions. And then you could imagine you have a high performance code and you could say in this particular usage context, you can make these assumptions. I'll just dig through my box of optimizations. Here's one that matches.
She makes a question.
Oh, did I know?
I think the question also applies without any volatile annotations or the like, in that if I really want to move a byte from one location, well, say I want to update to a particular byte in a storage location by adding one to it, I could do that by reading the whole word, updating the byte in the middle, and writing the whole word back, which might have the same cost or even be cheaper than just updating the byte, but in a sort of parallel, in a multi-threaded setting wouldn't be correct. So even in the absence of those annotations, I think there's still another sort of correctness criterion here.
Yeah, and there's an even more general way of, I think, stating that problem, which is that correctness is with respect to an execution model, right? So you're sort of identifying some of the nastier bits of a concurrent execution model. So if we had a particular application area in mind and we knew which of those assumptions we had to make, then we could put together a formal correctness check with respect to that definition of correctness. Or again, if we didn't know what assumptions you were making, we could just verify our code under n different definitions of correctness, annotate them, and squirrel them all away.
So in your preamble, you mentioned that this sort of addresses the problem after you've solved your memory movement choreography. Have you got a story for that? How do you deal with algorithms which are limited by a small cache and the way in which they manage that?
So that is, so there are many different granularities of optimization. What you're describing is an optimization at the granularity of memory traffic. The optimizations that we're primarily concerned with are a slightly smaller granularity than that. So I would say, as presented, this implementation isn't immediately applicable to that problem. Scope of kernel, or let me say it like this: the scope of kernels that we look at are between 10 and 100 lines of assembly, whereas memory effects like that typically take place at a much larger scale of implementation, which we can't consider. So I would say our approach is complementary to another tool which performs that type of optimization. Now that said, in principle, I don't think there's anything that restricts the use of this approach to only assembly level code, and it's possible that an implementation that was targeted at a slightly higher level, like the level of memory traffic, could work. You would just need, again, there's two parts to the story. There's a search part and there's a verification part. So you would need a tool for verifying that the transformations you were making are correct, and you would need a mechanism for searching through implementations that traded various performance properties with respect to memory movement.
Alex.
I was just going to say there are tools like FFTW and other special domain-specific tools that actually do these memory optimizations for particular kinds of applications. They're not stochastic; they're just doing brute force enumeration through some search space, but they do exactly what you described. Right.
Your variation function essentially is a form of point mutation. Did you consider whether there might be some plausible form of crossover that you could use to search the space better?
So let me make sure I understand that. The question is, or let me rephrase it differently. Let me try to rephrase the question in my own words. I showed you a set of transformations for exploring the space of programs. And I made no claim to you that these are the best possible transformations or the only transformations, and nor did I make a claim that they were minimal because, as I said, they were redundant. So the question is whether some sort of crossover transformation might be useful as well. And this is where I think you mean I have two code sequences. Let's imagine, and I take the first half of this code sequence and I bolt it on to the second half of this code sequence.
Right, and the reason why I asked about some form of crossover is doing it literally by just picking a point to cross over in initial and final sequences is probably not plausible, but there might be some way to divide the two and then remix the parts that is plausible.
There is a complication there, which is that there are, so I glossed over this, but we are, in proposing these random transformations, we are maintaining certain invariants in the code. So for instance, we're maintaining the invariant that we never read from an undefined location. And in doing mutations of this form, I think the likelihood that you break one of those invariants goes through the roof. So while this could be useful, particularly if we could constructively propose these transformations so that that invariant held, I think we could get some mileage out of it. But where the alternative is rejection sampling, basically putting two codes together, checking, no, undefined read, okay, throw it away, our proposal rate would drop substantially. We have the room until 4 o'clock, correct?
Yeah, I think so.
Until someone comes and kicks the door down. Yes. You come in with pitchforks.
I was wondering why bitwise correctness and not like normal correctness. Like if the correct answer is 1001, the answer 1000 seems more correct than the answer 1. I'm well outside my expertise here, so maybe it's a naive question.
No, I think that's actually a very good question. I think the general answer is there's a set of interesting application domains, and there's a set of cost functions. And some of those cost functions will be particularly well suited for some domains, and some will also be perversely poorly suited for other domains. And I don't think you'll ever be able to come up with a cost function that is well suited for all possible domains. What you're describing, I think the trick is in coming up with a cost function, matching a cost function to a domain in such a way that you're able to produce results, but you haven't also inadvertently limited the quality of those results by picking a cost function that somehow biases you away from an interesting part of the solution space. So for some applications, that might work perfectly well. In fact, that's basically another way of saying what our floating point correctness function was. The number of representable values between 1000 and 1001 is pretty close to the function you would get by just counting the number of integer values between 1000 and 1001. So not something we necessarily did. Primarily our fixed point benchmarks were cryptographic, and their bitwise equivalence is somehow more interesting, slightly more appropriate than integer. But you could just, again, you could just imagine a domain where integer comparison would be more appropriate. Sure.
All right, no more questions. Thanks, Eric.
All right, thank you.